Welcome back to my channel, and as always, thanks to my subscribers. Today I want to explain the basics of using classes in C++. As an example, I will use a traffic light simulated by an Arduino Nano and 6 LEDs, 2 red, 2 yellow, and 2 green. Here is the device. The LEDs are connected to the Nano by jumper wires. On the left side, the red LED anode is connected to pin 3, the yellow LED anode is connected to pin 4, and the green LED anode is connected to pin 5. All three cathodes are connected to the ground pin on the Nano. This device is therefore called a common cathode device. On the right side, the red LED cathode is connected to pin 6, the yellow cathode is connected to pin 7, and the green cathode is connected to pin 8. All three anodes are connected to the plus 5 volt pin on the Nano. Therefore, this device is called a common anode device. It may be hard to see them in the video, but there are current limiting resistors on all 6 LEDs. I will use the Arduino IDE, or Integrated Development Environment, to create the control program and to upload it to the Nano for testing. Refer to the comments below this video for guidance on downloading the Arduino IDE. The Arduino IDE uses the C++ programming language, so this will serve nicely to illustrate the basics of classes and objects in C++. Here is a program, or sketch, that one might use to control this device. Lines 1 through 3 define constants that set the timing of our traffic light. Lines 5 through 7 define the variables we will use to control our lights. Lines 9 through 17 define the setup function. This function is executed exactly once, immediately upon power-up of the Nano, or immediately upon uploading to the Nano. Lines 10 through 12 set the functions of pin 3, 4, and 5 to output, and lines 14, 15, and 16 set the output of those pins to low, or 0 volts, turning off the respective LEDs. Lines 19 through 36 define the loop function. This function is executed repeatedly following the setup function, and it continues to exit until the Arduino is powered down. Line 21 sets the output of pin 3 to high, or plus 5 volts, turning on the red LED. Line 22 pauses execution for 18,000 milliseconds. Line 25 turns the red LED off, line 26 turns the green LED on, and line 27 pauses execution for 15,000 milliseconds. Line 30 turns the green LED off, line 31 turns the yellow LED on, and line 32 pauses execution for 3,000 milliseconds. Finally, line 35 turns the yellow LED off. This returns the traffic light device to its original state, that is, all lights are turned off, to allow the cycle to begin again. By the way, this sketch and all the others I will show you are available online. See the description below the video for details. Once the sketch is complete, we can check it for errors. The compiler reports no errors, and so we can upload the program to the Nano. As expected, the lights begin to cycle on and off. This will continue until we alter the program or stop power to the Arduino. Now let's see how this same functionality can be provided by using a C++ class. A class is just a user-defined data type. Other examples of data types are integers, characters, floating point numbers, and strings. We describe a class by listing its data elements and its methods, which are simply class-specific procedures. Before I start, I'll save the sketch as a new file, classes2. We start by typing the keyword class, followed by the name of the class, in this case LED, followed by a pair of curly braces, and the second curly brace must be followed by a semicolon. We'll need to list all of the elements of our class inside those curly braces. In our example, we'll need three public methods. One is called LED. This method is called a constructor, and it provides the necessary code to initialize an instance of the class. The other two methods are called on and off. On turns on an LED, and off turns the LED back off. Last, we have one private data member called pin. This is the number of the pin on the Arduino which is connected to the LED. Since the pin number must be an integer between 1 and 21, at least for the Arduino Uno and Arduino Nano, we declare pin as an unsigned integer. Now that we have listed the methods in our class, we need to define them. They are defined the same as any other function in C++, except that the method name is preceded by the class name, LED, and 2 colons. The constructor does the following. First, it saves the pin number in the private data member pin with the leading underscore. Second, it calls the pin mode function to set the pin function to output. Third, it turns the LED off. Next, let's write the two functions that turn the LED on and off. This code looks exactly like the code we used in our first sketch. With our new LED class defined, we need to modify the rest of the code slightly. First, instead of defining three global integers, red, yellow, and green, we will define three global instances of the LED class, named red 1, yellow 1, and green 1. An instance of a class is called an object. These three lines declare objects of the LED class, the name of each object, and finally they invoke the class constructor to initialize each object. With that done, we no longer need the code in setup. All of that functionality has been embedded. We use the term encapsulated into the LED object. Finally, we now use the class methods on and off to turn the LEDs on and off. We have encapsulated the digital write function calls within the LED object. With all that done, we compile the program and see that it compiles with no errors. Now we can upload the program and we see that the traffic light simulator functions exactly as before. So why did we go to all that trouble? There are 3 reasons. First, the purpose of this video is to demonstrate how to create and use classes. But more importantly, the second reason is that classes allow you to encapsulate hardware-specific details. If you wanted to modify this program to operate on, say, a Raspberry Pi, you would only have to alter the code inside the class methods. The third reason is to make your programs more easily written and understood by encapsulating complex actions. We'll see examples illustrating both of these 2 reasons later in the video. Let's modify our program to control the second set of LEDs. We should be able to simply add 3 new objects, red 2, yellow 2, and green 2, and specify their pin numbers. First, of course, we'll change the name of this sketch to Classes 3. We add the declarations for red 2, yellow 2, and green 2. And we add code to turn these on and off. That was certainly easy, but when we upload the program, we immediately see that something is wrong. The second set of LEDs is operating backwards. When they should be on, they are off, and when they should be off, they are on. The problem lies in the fact that this device is wired with common anodes. This means positive voltage is always supplied to all 3 LEDs. To turn an LED on, we need to set the corresponding pin output to low, allowing current to flow. When we want to turn the LED off, we set the pin output to high. With positive voltage on both LED leads, no current can flow, and the LED goes dark. We will fix this by modifying our LED class. First, let's define 2 constants, common cathode and common anode. These will be used to specify how the LED is wired. Next, we'll add a second constructor method. We can use the same name because the formal parameter lists are different. This in turn means the compiler can determine which function we mean. This is called function overloading. Next, we'll define 2 more private variables, LED on and LED off. These will be set to the appropriate values of either high or low, depending on how the LED is wired. Now we need to alter the original constructor method to set the default values of LED on and LED off. The default assumes common cathode wiring. There's no reason for this choice, it's arbitrary. Now we revise the on and off methods to use LED on and LED off instead of high and low. Last, we need to write the new constructor method. It looks almost exactly like the first method, except we add a few lines of code to set LED on and LED off for common anode wiring. That's all the changes we need to make to the class. Now we revise the declarations of red 2, yellow 2, and green 2 to specify that they are wired with common anodes. We now check for errors and upload the program. And we can see that our changes have fixed the problem. The LEDs are now operating exactly as we wanted. I hope you can see the power of what we have done. The code to turn the LED on, for example, red 2.on, followed by parentheses, is unchanged. We simply changed how the class code handled that operation. Also note that we could have changed the declarations of red 1, yellow 1, and green 1 to specify common cathode wiring. The result is the same, but the source code now explicitly shows the way these devices are wired. Alert viewers who have been watching the inset noticed that the second yellow LED did not light as expected. Obviously, there's a bug. Let's see how hard it is to find. And there it is. We never turned the second yellow LED on, we just turned it off. The fix is easy, and now all the lights will operate as expected. But we're not done yet. We now have the computer equivalent of a utility worker standing at the traffic controller panel and switching the lights on and off manually. This works, but surely that worker could be doing other, more productive work. The same is true for the Arduino. I would guess that more than 99% of the time, the Arduino processor is idle as it waits out all of those delay instructions. An Arduino Uno, or a Nano, can control up to 21 different LEDs, but we're using it to control just 6. If only there was a way to automate the behavior of the LED class. Of course there is, and here's how. First, let's rename our sketch to Classes 4. We start by defining 3 new constants, LED on, LED off, and LED blink. These constants will be used by our class to determine the behavior of each individual LED. As you imagine, if an LED is in the LED on state, it will always be on. Likewise, if an LED is in the LED off state, it will always be off. Finally, if it is in the LED blink state, it will blink on and off repeatedly. But here is the key. We can change the state of any LED at any time by invoking the on, the off, or the blink methods. We need to list 3 new methods, 2 versions of blink and a refresh method. Next, we list the current state and the blink rate parameters in each object. Remember, every instance of the class has its own private data store. Now we have modified the LED class definition to list the new methods and the new data items. So we must modify the on and off methods so they simply change the value of the state variable. Then they call the refresh method. The refresh method handles all of the turning on and off of the LEDs in accordance with the LED state. Now it's time to write the blink methods. Like the on and off methods, blink changes the state of the LED to LED blink, but it also stores the values of on time, off time, and it stores the start time of the cycle. It also initializes the value of blink on, which determines whether the LED is currently on or off. Finally, just like on and off, blink calls the refresh method. We want two versions of blink. The first version immediately turns the LED on, then turns it off and on repeatedly. The second version will wait for a specified time before it turns on the LED. The two versions are almost the same, except we use the values of off time and delay to ensure the LED starts blinking at the desired time. Now it's time to write the refresh method. This method handles all three LED states, on, off, and blink, and naturally it handles each of them differently. For the on state, it turns the LED on. For the off state, it turns the LED off. For the blink state, it determines if the LED should be currently lit or unlit based on the value of blink on. If it should be lit, it turns the LED on. Then it checks to see if the LED has been on for the specified time. If so, it turns off the LED and starts the off cycle. If the LED is not supposed to be lit, blink turns the LED off, then checks to see if the LED has been turned off for the specified time. If so, it turns the LED back on and starts the on cycle. This completes the modifications to the LED class. Before moving on, I check the code and find and fix a few typographical errors. Finally, with all the errors fixed, we can move on to modifying the main portion of the code. These modifications are significant. The loop function now consists of nothing but calls to the refresh method of every LED. This ensures that each LED will be turned on or off at the appropriate times. The setup function now has a significant task. It starts all of the LEDs blinking according to the desired schedule. As a test, let's program the red 1 LED to blink on and off once a second. We'll program the yellow 1 LED to blink on for 1 second and off for 2 seconds, but the blinking won't start for 5 seconds. Finally, we'll program the green 1 LED to blink on and off approximately once every 1/3 of a second. We'll verify the program and upload it. And the LEDs begin flashing on and off exactly as we wanted. As you watch these LEDs flashing on and off completely independently, imagine how much harder it would be to program this behavior without using classes. At last, we can return to our original problem of controlling our simulated traffic light. The red 1 LED must be on for the red 1 duration. The yellow 1 LED must be on for the yellow on duration. And the green 1 LED must be on for the green on duration. The red 1 LED must be off for the yellow on plus the green on duration. The yellow 1 LED must be off for the red on plus the green on durations. And the green 1 LED must be off for the red on plus the yellow on durations. Now we need to determine the delays for the green 1 and the yellow 1 LEDs. The yellow 1 LED must delay while the red 1 LED and the green 1 LED are lit. And the green 1 LED must delay while the red 1 LED is lit. Now we can copy these lines to set up the cycles for the second set of LEDs. The only parameters we'll need to change are the delays for each LED. There is no delay for the green 2 LED. The yellow 2 LED must delay while the green 2 LED is on. And the red 2 LED must delay while the green 2 and yellow 2 LEDs are on. Oops, I almost forgot to change red 1 to red 2, yellow 1 to yellow 2, and green 1 to green 2. Once that's done, we upload the final program, and our traffic light simulator starts working as desired. As you watch our simulated traffic light, I will summarize what I hope I have demonstrated in this video. First, I have shown you how to create a class in C++ and how to declare objects which are members of the class. Second, I have shown you how to provide overloaded functions to allow the programmer, that's you, to specify optional additional arguments. Third, I have shown you how to invoke class-specific methods on a particular object, for example, red1.refresh. Fourth, I have shown you how you can automate the behaviors of your objects. Finally, I have shown you how classes can allow you to encapsulate hardware-dependent code into one spot which can easily be modified without touching the main program. The class's for listing need not be the end. You can always add more methods to the LED class. For example, Arduino pins 3, 5, 6, 9, 10, and 11 on the Arduino support pulse width modulation, or PWM, which allows you to make your LEDs less bright. See if you can add a dim method to the class. Perhaps you could add a ramp method, specifying a starting brightness, an ending brightness, and a ramp time. The possibilities are endless. As always, I would love to hear your comments and questions. If you want to see more videos of this type, be sure to subscribe and hit that like button. Thanks for watching, and I'll see you next time.